RTD, or Resistance Temperature Detector, relays offer temperature monitoring and protection for motors by sensing excessive winding temperatures. RTD relays trip when the winding temperature goes beyond a preset limit, generally higher than what overload and stalling relays monitor. Overload relays guard against sustained overcurrents leading to overheating but might miss fast temperature changes from faults or insulation issues. Stalling relays protect against extended low speed or high torque conditions that cause overheating but may not catch localized winding temperature increases. RTD relays offer extra protection where overload and stalling relays might fall short. Firstly, rapid temperature change detection. RTD relays react to quick temperature spikes from faults, short circuits, or insulation failures faster than overload or stalling relays. Secondly, localized heating detection. RTD relays directly monitor winding temperatures, spotting localized heating from winding faults or poor ventilation that current or speed-based relays might miss. Thirdly, higher temperature protection. RTD relays protect at higher temperatures, preventing severe motor damage from extreme heat. Fourthly, early warning system. RTD relays act as an early alert for temperature issues, enabling maintenance to intervene before a failure. In summary, while overload and stalling relays are important, RTD relays add value by directly monitoring winding temperatures and protecting against rapid changes, localized heating, and high temperatures. Combining RTD relays with overload and stalling relays improves protection and boosts the reliability of 3,300 volts motors. Specifically, overload relays primarily detect and respond to sustained overcurrent conditions, which can lead to overheating of the motor windings. These relays typically operate based on the root mean square value of the current, providing a measure of the thermal stress in the motor. However, overload relays might not be sensitive enough to detect rapid temperature changes caused by internal faults, such as short circuits or insulation breakdown within the motor windings. These faults can cause localized heating and damage to the motor insulation before the overload relay has time to react. Stalling relays, on the other hand, are designed to protect the motor against prolonged low speed or high torque conditions. These conditions can occur when the motor is overloaded or when the driven equipment experiences a mechanical failure, causing the motor to draw excessive current and generate heat. Stalling relays typically operate based on the motor's speed or current, tripping the motor if it remains in a stalled condition for a predetermined period. However, stalling relays may not be effective in detecting localized temperature rises in the motor windings that are not directly related to the motor's speed or torque. For example, a winding fault or poor ventilation can cause localized heating and damage to the motor insulation without necessarily causing the motor to stall. RTD relays provide additional protection by directly monitoring the temperature of the motor windings. RTD are temperature sensors that are embedded within the motor windings to provide a direct measurement of the winding temperature. RTD relays use these temperature measurements to trip the motor if the winding temperature exceeds a predetermined set point. This set point is typically higher than the operating temperatures monitored by overload and stalling relays, allowing the RTD relay to provide protection against rapid temperature changes, localized heating, and higher temperatures that may not be detected by the other relays. One scenario where RTD relays can provide additional protection is in the event of a rapid temperature increase caused by a fault or short circuit within the motor windings. In this case, the RTD relay can detect the rapid temperature increase and trip the motor before the overload or stalling relay has time to react, preventing further damage to the motor. Another scenario where RTD relays can provide additional protection is in the event of localized heating caused by a winding fault or poor ventilation. In this case, the RTD relay can detect the localized heating and trip the motor before the temperature rises to a level that could cause catastrophic damage to the motor insulation. In addition to providing protection against faults and abnormal operating conditions, RTD relays can also provide an early warning system for developing temperature problems. By monitoring the winding temperature over time, maintenance personnel can identify trends and patterns that may indicate a potential problem. This allows them to take corrective action before a fault occurs, such as improving ventilation or repairing a winding fault. The installation of RTD relays in conjunction with overload installing relays can significantly enhance the overall protection and reliability of 3300 volts motors. While overload installing relays provide valuable protection against overcurrents and prolonged low speed or high torque conditions, RTD relays offer additional benefits by directly monitoring winding temperatures and providing protection against rapid temperature changes, localized heating, and higher temperatures. The combination of these three types of relays provides a comprehensive protection system that can help to prevent motor damage and ensure the reliable operation of critical equipment. Consider a motor operating at a facility powering a critical pump. The motor is equipped with overload installing relays set to protect it from overcurrent and stall conditions respectively. One day, due to a partial blockage in the pump, the motor starts experiencing increased load. The overload relay, sensing the higher than normal current, begins to heat up, but the current is not high enough to immediately trip the relay. Simultaneously, a localized hotspot starts developing in one of the motor windings due to insulation degradation. This hotspot is not detectable by the overload relay, as the overall current draw hasn't exceeded its set limit significantly. The stalling relay also remains inactive, as the motor speed is still within the acceptable range. However, the temperature in the localized hotspot continues to rise rapidly. Without an RTD relay, this situation could escalate quickly. The insulation in the hotspot would continue to degrade, leading to a short circuit and eventually a catastrophic motor failure. This would result in the pump shutting down, causing a disruption in the facility's operations. Now, consider the same scenario with an RTD relay installed. As the temperature in the localized hotspot rises, the RTD sensor detects the increase and sends a signal to the RTD relay. The RTD relay, programmed to trip at a specific temperature threshold, activates and shuts down the motor. This intervention prevents the insulation from completely failing and avoids a major motor breakdown. Maintenance personnel can then investigate the cause of the hotspot, repair the winding insulation, and clear the blockage in the pump before resuming normal operations. The RTD relay, in this case, provided an additional layer of protection that the overload installing relays couldn't offer. It detected a condition that was specific to winding temperature and acted quickly to prevent a more serious failure. The set point of the RTD relay is a critical parameter that determines its effectiveness. It should be set high enough to avoid nuisance tripping during normal motor operation, but low enough to provide adequate protection against overheating. The appropriate set point will depend on the motor's design, operating conditions, and insulation class. Another important consideration is the placement of the RTD sensors within the motor windings. The sensors should be located in areas that are most susceptible to overheating, such as the end windings or the stator slots. The number of sensors used will also depend on the motor's size and complexity. For large motors, it may be necessary to use multiple sensors to provide comprehensive temperature monitoring. RTD relays offer several advantages over other types of temperature monitoring devices. Firstly, they provide a direct measurement of the winding temperature, which is more accurate than indirect measurements based on current or speed. Secondly, they are relatively immune to noise and interference, making them suitable for use in harsh industrial environments. Thirdly, they are easy to install and maintain. NEC Article 430.126 covers motor thermal protection. Selecting the appropriate RTD relay and configuring its settings requires careful consideration of the motor's characteristics and operating conditions. Consulting with a qualified electrical engineer or motor specialist is recommended to ensure that the RTD relay is properly installed and configured for optimal protection. By investing in RTD relays, facilities can enhance the reliability of their motors, reduce the risk of costly downtime, and improve the safety of their operations. The enhanced protection offered by RTD relays justifies their installation, especially in critical applications where motor failure can have significant consequences. The cost of an RTD relay is relatively low compared to the cost of repairing or replacing a motor, making it a worthwhile investment. Furthermore, the early warning capability of RTD relays can help to prevent costly unscheduled downtime by allowing maintenance personnel to address potential problems before they lead to a failure. The use of RTD relays is not limited to 3300 volts motors. They can be used to protect motors of all sizes and voltages. However, they are particularly beneficial for large or critical motors where the consequences of a failure are significant. In addition to protecting motors from overheating, RTD relays can also be used to monitor the temperature of other electrical equipment, such as transformers and generators. This can help to prevent failures and extend the lifespan of the equipment. The application of RTD relays is not limited to industrial settings. They can also be used in commercial and residential applications to protect motors in equipment such as HVAC systems and appliances. In conclusion, RTD relays provide a valuable layer of protection for motors and other electrical equipment. Their ability to directly monitor winding temperatures and provide early warning of potential problems makes them an essential component of a comprehensive protection system. By investing in RTD relays, facilities can enhance the reliability of their equipment, reduce the risk of costly downtime, and improve the safety of their operations. Some additional information about RTD construction and operation follows. RTD are temperature sensors that exploit the predictable change in electrical resistance of some materials with temperature. They are commonly used in industrial temperature measurement due to their accuracy and stability. The sensing element in an RTD is a resistor that changes its resistance value with temperature. The most common type of RTD is the platinum RTD, which uses platinum as the resistive element. Platinum is chosen for its high accuracy, stability, and wide temperature range. Other materials, such as nickel, copper, and alloys, can also be used, but they typically have lower accuracy or stability. RTD are available in various configurations, including wire wound, thin film, and coiled elements. Wire wound RTD are made by winding a fine wire of platinum around a ceramic or glass core. Thin film RTD are made by depositing a thin film of platinum onto a ceramic substrate. Coiled elements are made by coiling a platinum wire into a spring-like shape. The resistance of an RTD increases linearly with temperature. The relationship between resistance and temperature is described by the following equation: R equals R0 times 1 plus alpha times T, where R is the resistance at temperature T, R0 is the resistance at 0 degrees Celsius, alpha is the temperature coefficient of resistance, and T is the temperature in degrees Celsius. The temperature coefficient of resistance alpha is a material property that describes how much the resistance changes per degree Celsius. For platinum, alpha is approximately 0.385 ohms per ohm per degree Celsius. RTD are typically used in a full wire configuration to eliminate the effects of lead wire resistance. In a full wire RTD, 2 wires are used to supply current to the RTD, and 2 wires are used to measure the voltage drop across the RTD. This configuration allows the resistance of the RTD to be measured accurately, regardless of the resistance of the lead wires. 3-wire RTD are also available, but they are less accurate than 4-wire RTD. In a 3-wire RTD, 1 wire is shared between the current supply and voltage measurement. This configuration can introduce errors due to lead wire resistance, especially if the lead wires are long or have different resistances. RTD circuits are typically used with signal conditioning circuitry to amplify and linearize the RTD signal. The signal conditioning circuitry also provides excitation current to the RTD and compensates for lead wire resistance. The output of the signal conditioning circuitry is typically a 4 to 20 mA current signal or a 0 to 10 volts voltage signal, which can be easily interfaced with a control system or data acquisition system. RTD are available in a wide range of temperature ranges from -200 degrees Celsius to +850 degrees Celsius. They are also available in various accuracy classes, with accuracies ranging from plus or minus 0.1 degrees Celsius to plus or minus 1 degree Celsius. The accuracy of an RTD depends on the quality of the platinum, the construction of the sensing element, and the calibration of the RTD circuit. RTD are relatively stable over time, but they can drift slightly due to aging or exposure to extreme temperatures. To maintain accuracy, RTD should be calibrated periodically. The calibration process involves comparing the RTD reading to a known temperature standard and adjusting the RTD circuit to compensate for any drift. RTD are commonly used in a variety of industrial applications, including temperature measurement in chemical processes, food processing, pharmaceuticals, and power generation. They are also used in HVAC systems, appliances, and medical equipment. The choice of RTD for a specific application depends on the temperature range, accuracy requirements, and environmental conditions. Platinum RTD are generally preferred for high-accuracy applications, while other materials, such as nickel or copper, may be used for less demanding applications. The physical construction of the RTD, such as wire wound or thin film, will also depend on the application requirements. Wire wound RTD are more rugged and can withstand higher temperatures, while thin film RTD are smaller and more accurate. RTD installation is also critical for accurate temperature measurement. The RTD should be installed in a location that is representative of the temperature being measured. It should also be protected from mechanical damage, moisture, and corrosive environments. The lead wires should be properly shielded and grounded to minimize noise and interference. In summary, RTD are accurate, stable, and reliable temperature sensors that are widely used in industrial and commercial applications. Their predictable change in resistance with temperature allows for precise temperature measurement. The selection, installation, and calibration of RTD are critical for ensuring accurate temperature measurement. RTD provide a valuable means of monitoring motor winding temperatures for enhanced protection and reliability. The 4-wire configuration is the most accurate method for measuring the resistance of an RTD because it eliminates the effects of lead wire resistance. This is particularly important when the RTD is located far from the measuring instrument, as the resistance of the lead wires can be significant. In a 4-wire RTD, 2 wires are used to supply current to the RTD, and 2 separate wires are used to measure the voltage drop across the RTD. The measuring instrument only measures the voltage drop across the RTD sensing element and does not include the resistance of the lead wires. This eliminates any error caused by the lead wire resistance. The resistance of the lead wires can vary with temperature, which can further affect the accuracy of the measurement. The 4-wire configuration eliminates this error by measuring the voltage drop across the RTD sensing element independently of the lead wire resistance. 3-wire RTD are a compromise between accuracy and cost. They are less accurate than 4-wire RTD because they do not completely eliminate the effects of lead wire resistance. However, they are less expensive to install and maintain than 4-wire RTD. In a 3-wire RTD, 1 wire is shared between the current supply and voltage measurement. This introduces an error because the measuring instrument measures the voltage drop across the RTD sensing element plus the resistance of one of the lead wires. The accuracy of a 3-wire RTD can be improved by using lead wires with low resistance and by calibrating the measuring instrument to compensate for the lead wire resistance. However, it is not possible to completely eliminate the effects of lead wire resistance with a 3-wire RTD. 2-wire RTD are the simplest and least expensive type of RTD. However, they are also the least accurate. In a 2-wire RTD, the same 2 wires are used to supply current to the RTD and to measure the voltage drop across the RTD. This means that the measuring instrument measures the voltage drop across the RTD sensing element plus the resistance of both lead wires. The resistance of the lead wires can significantly affect the accuracy of the measurement, especially if the lead wires are long or have high resistance. 2-wire RTD are typically only used in applications where accuracy is not critical. The choice of RTD configuration depends on the accuracy requirements of the application. 4-wire RTD are the most accurate and are recommended for applications where high accuracy is required. 3-wire RTD are a good compromise between accuracy and cost. 2-wire RTD are the least accurate and are only recommended for applications where accuracy is not critical. In addition to the number of wires, RTD are also available in different accuracy classes. The accuracy class of an RTD is a measure of its accuracy over its entire temperature range. The most common accuracy classes are Class A, Class B, and Class C. Class RTD are the most accurate and have the tightest tolerances. Class B RTD are less accurate than Class RTD, but they are also less expensive. Class C RTD are the least accurate and have the widest tolerances. The choice of accuracy class depends on the accuracy requirements of the application. The process of selecting an RTD relay, one should consider several key factors to ensure optimal motor protection and reliable operation. Firstly, carefully evaluate the motor's operating characteristics, including its rated voltage, current, speed, and load profile. This will help determine the appropriate temperature set points for the RTD relay. Secondly, the type and number of RTD sensors embedded in the motor windings are important considerations. Ensure that the RTD relay is compatible with the sensor type e.g., tone 100, tone 1000 and can accommodate the number of sensors installed. Thirdly, select an RTD relay with adjustable temperature set points to allow for customization based on the motor's specific operating conditions. The relay should also have adjustable time delays to prevent nuisance tripping due to transient temperature fluctuations. Fourthly, consider the communication capabilities of the RTD relay. Some relays offer Modbus or other communication protocols for remote monitoring and control. This can be beneficial for integrating the RTD relay into a larger control system. Fifthly, choose an RTD relay from a reputable manufacturer that has a proven track record of reliability and performance. Read reviews and compare specifications to ensure that the relay meets the application requirements. Sixthly, ensure that the RTD relay complies with relevant industry standards such as IEC 60947-4-1 or UL 508. This will help ensure that the relay is safe and reliable. Seventhly, select an RTD relay with a user-friendly interface for easy configuration and monitoring. This will simplify the installation and maintenance process. Eighthly, ensure that the RTD relay is compatible with the motor's existing protection system, including overload relays and stalling relays. The RTD relay should work in coordination with these other devices to provide comprehensive motor protection. Ninthly, consider the environmental conditions in which the RTD relay will be installed. Choose a relay that is designed to withstand the temperature, humidity, and vibration levels in the environment. Tenthly, consult with a qualified electrical engineer or motor specialist to ensure that the RTD relay is properly selected and configured for the application. This will help ensure that the motor is adequately protected and that the RTD relay operates reliably.